Hey, yo! Down here. Yo, what's up? Hey, I got that stuff you were looking for right here. You're the one that wanted to build your own Starship Flame Trench, right? No? What the fuck? Well, since you're here, I'm gonna show you how to do it anyways. Today, we're gonna go through the step-by-step process of building a massive subsurface flame trench. And just to make things a little more interesting, we're gonna do it in a swamp. After that, we're gonna learn what makes this 250,000 gallon per minute water deluge system so unique. When we compare this to what everyone else has been doing over the last 66 years of space exploration, you may end up wondering, how was SpaceX the first one to come up with this? Considering this technology was patented in the same year as the beginning of the space race, it's hard to believe no one else has ever attempted to use it for this purpose. And who knows, maybe they never will. Because what if I told you that this is actually mid-level genius compared to the insane system that they developed for their brand new Starship launch pad? Yeah, you might want to sit down, because we've got a lot to cover. My name is Zach Golden, and this is another CSI Starbase Deep Dive Investigation. Hey everyone, welcome, and thanks for joining us. You know, when it comes to developing a brand new launch vehicle, whether you're a startup company or a legacy launch provider, there's a list of major engineering challenges that you're guaranteed to have to solve along the way. First, you need to develop an engine and a reliable way of testing it under flight-like conditions. Then you need to develop the manufacturing process for rapid mass production. More often than not, you may have to develop a second engine that's specifically tuned for vacuum operations. You need one second stage vehicle to get your payload into orbit, and one or sometimes multiple first stage boosters to provide the initial thrust needed to lift the second stage off the ground and propel it through the lower atmosphere. Just like the engines, you need to develop the facility and systems for manufacturing those vehicles and testing them on the ground. To test and launch those vehicles, you need a propellant storage and distribution system, a method of horizontally or vertically integrating vehicles and payloads, a transportation system, and of course a launch pad. With so many complex engineering challenges to deal with and a limited amount of resources on hand, it's only natural to look for every opportunity to take existing solutions, aka tried and true methods, and then integrate them at the proper scale for your specific needs. Now, the main focus of this video is water deluge systems. When you think of all the components that go into developing a launch pad, water deluge systems are basically just a small but important subcomponent of the overall launch system. It also happens to be one of those areas where it's extremely easy to go with the industry standard and just do what everybody else is doing. Of course, every launch pad is going to have its own unique flame deflector and water deluge system design based on the requirements of the vehicle. But the method for actually delivering that water to the launch pad is almost always going to be done one of two ways. Well, unless you're SpaceX. Ignoring all the other cool stuff they do, coming up with innovative water deluge system designs is kind of their thing. They've done it on 3 separate occasions now, and the latest one is on my short list for being one of the wildest ideas I've ever seen them come up with. But before we can discuss the crazy system they designed for their brand new Starship launchpad, we need to understand how we got here. And that brings us to the Massey's test site, home of the first of its kind Starship Flame Trench. I originally planned to start this episode out with a brief history of the evolution of the Massey's test site. But in the process of writing that summary, it ended up turning into an entire episode. So if you missed that, make sure to check it out here. Now, before we get started, let me address the elephant in the room. I know that some of you may be wondering, wait, didn't SpaceX commission this flame trench last year? Why wait to cover it now? Well, to be honest, this episode has been in the works for about a year and a half and has been interrupted on multiple occasions by other topics that I felt were a bit more time sensitive. But in my opinion, this has become even more relevant now as SpaceX is nearing completion on their second generation Starship launch pad. In order to truly appreciate what makes it such a massive leap in sophistication, we need to understand the important steps that came before. Now, with that said, you might expect that it would be extremely difficult to keep track of all of the little details I intended to cover after such a long time. Well, I certainly have many tools to help me stay organized, but perhaps the most important of those tools is my internet browser. Over the years, I've gone back and forth using nearly every internet browser in existence. But since I found Opera, I can't imagine using anything else. which is why I'm excited to partner with them for this episode. One of my favorite Opera features are the tab islands, which allow you to group related tabs together. For example, in the workspace I created for this episode, I have a huge number of tabs related to different topics I've been researching. With so many tabs, it can get quite difficult to navigate when I'm looking for something specific. But with Opera's tab islands, I can take everything related to Stennis Space Center, Cape Canaveral, various construction processes, and equipment spec sheets, and group them all into their own islands. Then I can instantly bring order to chaos by collapsing or expanding them as I navigate between different topics. Thanks to the awesome split screen feature, I can keep my episode script displayed on one side of the screen while I have whatever website I'm using for research on the other side. This eliminates the need for using multiple windows, which can get pretty distracting. If I encounter something I need additional information on while researching through various articles, I can use a quick keyboard shortcut to access Aria, the free built-in AI tool. Aria swiftly summarizes and expands on any topic right there in your browser. Aria also has a powerful image recognition ability, which allows me to upload any image and ask it to identify the object. This saves me countless hours of research time. If you're anything like me, then long work sessions are much more productive if I have a soundtrack in the background. With the built-in music player, I can choose from 7 different streaming platforms like Apple Music and bust out my favorite playlists. To control the music without interrupting my browsing, I can detach the floating player and place it anywhere inside or outside of the browser window. These features are crucial for helping me stay in the flow while I'm deep in the trenches working on these episodes. So if you're one of those people who keeps 500 browser tabs open at the same time, then it's time for you to level up. Download Opera today by clicking the link in the description and check it out for yourself. All right, with that, let's get into today's deep dive investigation. When the teams responsible for designing test stand infrastructure began planning to relocate ship static fire testing away from the launch complex, they knew they would have to do things differently. It was time to level up from this version 1 test stand. First and foremost, they could no longer afford to fire 6 extremely powerful liquid-fueled rocket engines from 8 meters above a flat surface. Not only was this counterproductive towards having a test stand that could handle hundreds of static fires without refurbishment, but there was simply not enough space to be dishing out flames in a 360-degree pattern at this small remote testing facility. So they needed a reliable way to redirect the flames away from the vehicle, which meant they would have to incorporate some type of flame diverter. Most flame diverters are constructed above grade and include a large raised structure for supporting the vehicle. SpaceX had already considered this type of test stand in the past with their original design for the Starship test stand at LC-39A in Florida. But there's a big logistical problem with these types of elevated structures in that they require large cranes to lift the vehicle on and off the test stand. This was something they were already doing at the time, but wanted to get away from. To meet this important design constraint, they would need a surface-level test stand, which meant the flame deflector would need to be below grade in a flame trench. This was something they already had plenty of experience with at their McGregor testing facility. But building an underground flame trench 250 miles inland in a location with dense cohesive soils and high natural stability is a lot different than building one here. Situated in a low coastal plain with marshes, tidal flats, sandy soils, and elevations barely above sea level, Boca Chica as a whole is easily one of the least ideal locations for building heavy industrial structures. As SpaceX has discovered on multiple occasions, if you don't perform a massive amount of groundwork to stabilize the soil, then any structure you build here is pretty much guaranteed to have issues later on. The Massey's test site in particular presents a unique challenge due to the fact that it's completely surrounded by water. Without having access to geotechnical or groundwater surveys for the site, we can't say for sure how deep the water table is. But typically, areas like this have extremely shallow water tables, which can be as little as 3 feet below the surface. The depth of the water table can change during periods of heavy rain and also during high and low tides. This presents a significant problem for subsurface structures, especially if that structure is essentially a gigantic empty swimming pool. If you build an in-ground swimming pool in an area with water-saturated soils without doing something to mitigate ground conditions, then there's a good chance that you will eventually wake up one day to a rather unpleasant surprise. Those of you who own a backyard pool may be familiar with the pool pop phenomenon. If so, hopefully you know what that is from being educated on how to prevent it and not from personal experience. Pool pop occurs when hydrostatic pressure from groundwater exerts an upward pressure on the shell of the pool. If the pool is empty or partially filled, the buoyancy force can lift it out of the ground. This usually happens after heavy rainfalls or rapid snowmelt. Now, a flame trench for a rocket of this size is obviously going to be far more substantial than a simple swimming pool. But the fact that it's constructed with thousands of tons of concrete does not make it immune to hydrostatic pressure. Concerns like this are part of the reason why, for several years, many people believed it wasn't possible for SpaceX to build a flame trench at Starbase. In reality, as long as you figure out the right way to do it, it's actually fairly easy to pull off. So, the first and arguably most important step for constructing the Starship Flame Trench at Massey's was to stabilize the soil. The typical solution that SpaceX uses to increase the load-bearing capacity of the soil beneath structures that have to support hundreds, if not thousands of tons, is to use a pattern of continuous flight auger, or CFA pilings for short. At the Massey's test site, these CFA pilings were used when constructing the foundation for the Starship and booster cryo-testing stations, and also for the massive liquid oxygen storage tanks. Not only do these CFA piles help increase the load-bearing capacity beyond what the native soil is able to support, but they also help anchor structures into the ground and provide resistance against uplifting forces. While this would certainly have been a viable solution here, on its own, it doesn't eliminate groundwater saturation, which would still be a problem during the construction process. The last thing you want is for groundwater to penetrate through the sidewalls or seep up through the floor of the trench during excavation. To address this situation, civil engineers decided to employ a fairly common ground remediation process known as deep soil mixing, or DSM for short. DSM is a method of providing settlement control and increasing load-bearing capacity in soft soils. This process makes use of a material that many of you may have personal experience with if you happen to have one of these psychopathic creatures running around your home. The material I'm referring to is, of course, kitty litter. One of the main components of kitty litter is a substance known as bentonite. Bentonite is the ideal base material for kitty litter because of its ability to absorb moisture and liquid. When in contact with liquids, bentonite can absorb up to 3.5 times its own weight, causing hard clumps to form, which are then easily scooped up. When used in soil remediation applications, bentonite can create impermeable layers of hardened soil that will prevent water from penetrating through to the excavation area. In mid-November of 2023, equipment for the on-site slurry mixing plant began to arrive to the Massey's outpost, along with 70 super sacks of bentonite clay. Each of these sacks weigh 3,000 pounds, or 1.5 tons. That's more than 100 tons total. At the beginning of December, the nearly 2-month-long job of mixing this bentonite into the soil began. Let's take a look at how this process works. Starting off at the mixing plant, the super sacks of sodium bentonite are blended with water to create a viscous, mud-like slurry. Using a rotary drilling rig, a specialized mixing blade is attached to the hollow rotating Kelly bar. At the top of the shaft, there's a hose which supplies the slurry as it's pumped over from the mixing plant. The mechanism incorporated into the mixing blade atomizes the slurry by injecting it into a flow of air as it's being discharged. Once the mixing blades begin cutting through the soil, the atomized slurry helps to loosen the soil and reduce the downward force required to penetrate through the various levels of material. When the bentonite is injected under pressure like this, it will actually spread out further than the diameter of the column. This bentonite-infused soil mixture is commonly referred to as soilcrete, and once dried, it will act as a barrier to prevent groundwater from penetrating through. Based on the configuration of the BG-45 drilling rig, we were able to estimate that these columns of soilcrete likely extend up to 72 feet into the ground. This is roughly 22 feet below the eventual bottom of the flame trench. Typically, these columns are drilled in some sort of predetermined pattern based on the needs of the structure it will be supporting. In this case, from what we have been able to determine based on the weekly RGV aerial flyovers during the 2-month period that this operation was taking place, it appears that these columns covered the entire surface area of the flame trench. The columns also extend beyond the footprint of the trench walls, which we will be able to see shortly. While it's difficult to verify, I believe that they went back and drilled additional columns between each of the rows. By overlapping the columns, they effectively created a massive 230-foot long, 69-foot wide, and 72-foot deep solid block of soilcrete. Alright, now that we've covered the initial ground preparation, let's move on to the actual flame trench. As you may have noticed while I was going through images from the previous section, the construction for the walls of the flame trench actually began long before the deep soil mixing process was even finished. By overlapping these two operations, they shaved nearly 2 months off of the construction time of this new test stand. Had they not done it this way, it would have been a significant setback for operations at the launch complex. As I mentioned in the Evolution of Massey's episode, SpaceX was depending on this test stand becoming operational as soon as possible so they could dismantle the suborbital test stands and begin constructing the second orbital launch pad. They were only planning on flying a set number of missions with the current generation of Starship, and the next generation vehicles would not be compatible with the original launch mount. So it was mission critical for the new launch pad to be ready in time for the first V3 ship and booster flight. To avoid the risk of causing delays to the launch schedule more than a year and a half in the future, they managed to shorten the construction timeline by finding ways to overlap various construction operations wherever it was possible. I can only imagine that balancing all of these interdependent activities was probably a nightmare for the project management team. After the deep soil mixing process was completed on the northern half of the flame trench, it was time to begin constructing the diaphragm walls. Commonly referred to as slurry walls, these continuous, watertight, and structurally robust walls are constructed by excavating a deep, narrow trench and filling it with reinforced concrete or slurry. They are built in panels to ensure continuity and are often used in challenging soil conditions or near water to provide stability and prevent groundwater seepage. There are many applications for these walls, but some of the more common usages are for supporting deep basements or underground parking structures for high-rise buildings. You can also find them used to form walls for large underground tunnels, and they are often a key component in the construction of dams, where they act as a cutoff wall to prevent water from seeping under the dam or as structural supports for spillways. On December 12th of 2023, workers began placing the formwork for the first of what are known as guide walls. As the name implies, these guide walls are used to keep the excavation tool properly aligned to ensure the diaphragm wall is constructed in a straight line. Using humans for scale, you can see that the trench created for the walls is actually fairly shallow. They are typically about 3 to 5 feet deep. Once the formwork is in place, concrete is poured on either side. After it's hardened to an acceptable level, the formwork is removed and the void space between the walls is temporarily filled back in with dirt. I think this is just to reduce the likelihood of people falling into the trench. While this was ongoing, another crew was busy assembling the massive rebar cages that would later be used to reinforce the walls. The next step in the process is to begin excavating sections of the wall slightly wider than the width of the rebar cages. For this, they use a hydraulic clamshell excavator, which is also referred to as a grab bucket. The grab bucket is suspended from a crane and lowered between the guide walls to begin removing material. To ensure the walls are as straight as possible, the hydraulic grab has steering plates which push against the guide walls to control the alignment as they go down. The walls of the freshly excavated trench are then used to continue guiding the tool as they progress further. It's important to note that the walls of the trench are within the footprint of the soilcrete block. As I mentioned before, this prevents water from penetrating through the walls as material is being removed. As an additional precaution, during the excavation process, a thick bentonite slurry is pumped into the holes. The density of the slurry helps to temporarily reinforce the walls of the trench to prevent them from collapsing. If the grab bucket reaches harder bedrock layers of the earth, then the clamshell excavator can be swapped out for a hydromill cutting tool until they are able to penetrate through it. From what I can tell, that didn't appear to become necessary for this particular job, but I think it's still worth mentioning. That way, if you decide to build one of these in your backyard, you know how to handle this particular situation. After reaching the desired depth, end stop plates, like the one shown here, are lowered to the bottom of the trench and rest against the walls on either side. These create a smooth barrier between the adjacent zones. Next, the massive rebar cages are carefully lowered into the hole. These cages are roughly 100 feet long, which means the wall panels extend around 32 feet below the massive block of soilcrete, and 40 feet below the eventual floor of the trench. Instead of allowing the rebar cages to rest at the bottom of the hole, metal beams are used to suspend the cage so the top will remain exposed to allow additional rebar to be tied into it later for the surface level structures. Once secured, concrete is injected into the bottom of the hole. As the heavier concrete is being poured, it displaces the slurry mixture, which is continuously sucked out until only concrete remains. While they wait for the concrete for the first wall panel to harden, they will skip over the second zone and begin excavating the third. This pattern is continued until they reach the end of the guide wall. At this point, the concrete for panels 1 and 3 should be hardened to a sufficient level, and they can come back and start the even-numbered panels. While excavating the zones between the two completed panels, it's important to make sure that the edges of either wall are completely cleaned before moving on to the next step. If any soil remains stuck to the edges of the wall, then it could result in gaps between the panels. This is where those end stop plates that I mentioned previously come into play. Instead of using the grab bucket to scrape against the concrete walls, the end stops create a void space between the hardened concrete and the soil. As an added bonus, the end stop plates can be designed to slot into the side of the excavation tool. That way, when the clamshell is opened, it can scrape along the steel beam instead of the concrete. Once the zone is fully excavated, the end stop panels can be removed. Another benefit of the end stops is that they can be designed in a T-shape like this one, so that once it's removed, it leaves behind a slot down the middle of the previously completed panel. As a result, when the concrete is poured into Zone 2, it will fill the slots on either side and create interlocking panels. This reduces the likelihood of the walls being pushed inwards towards the middle of the trench. At this point, I think the soilcrete outside of the perimeter of the wall is no longer serving a purpose, but the block contained within the walls will prevent water from seeping up from below. While these animations from Ryan Hansen's Space are extremely helpful for visualizing this process, if we wanted to be more accurate, we would show the deep soil mixing and diaphragm wall construction processes overlapping each other. Instead, we're showing them in sequential order of how they would have been constructed if SpaceX wasn't in a massive rush to complete this. As soon as the walls on the northern side of the trench were completed, it was time to begin constructing the above-ground portion of the flame trench. In mid-February, roughly 3 months after the start of the project, crews began forming the square opening for the mouth of the trench. The first step was pouring a 6-inch thick, non-reinforced square pad where the mouth would be. This is normally referred to as a blinding or working layer and is basically used to create a flat, uniform surface for forming out the grade beams. As I mentioned earlier, you can see the ends of the rebar cage from the diaphragm wall penetrating up through the working layer to allow the walls to be structurally tied into the grade beams. Before adding the rebar cages, they had to place all of the steel embed plates that would later remain exposed on the outside of the concrete. Embed plates are used as mating surfaces for welding additional steel support structures onto the wall. The alternative is drilling anchor bolts into the concrete after it's hardened, which is less ideal if it can be avoided. As you can see, there are 4 large embed plates in each corner of the opening. This is where the pedestals for the static fire stand would later be attached. Less noticeable here are the long embed plates mounted halfway up the formwork wall. These were later used for mounting the railing that the sliding platform will move across as it's extended out over the mouth of the trench. There are additional plates that form a rim around the top and bottom edges of the opening. We will discuss those more later. For mounting the ship QD Gantry, there are 4 embed plates on the southern side of the grade beams. And finally, there are 8 embed plates on the first portion of the roof platform of the trench, which I haven't figured out the purpose for yet. With all of this in place, they were able to fill these sections in with concrete and move on to the rest of the trench. For this next section, they formed out the remaining roof and the grade beams for the side walls of the trench. Just like the mouth of the trench, this started off with a 6-inch pile cap on top of both walls. An interesting detail that we didn't realize until recently is that the ceiling of the trench is not flat as we initially believed. Thanks to the yellow vapor barrier underneath the rebar, you can see that it slopes downwards on the edges where the roof meets the wall. This angled transition is likely intended to reduce stress concentrations at the junction of the wall and ceiling and distribute forces more evenly. It should also help to promote smoother flow of steam and exhaust gases exiting the trench and minimize direct impingement and erosion of the surfaces. Just like the first section of the roof, there are embed plates for the guide tracks for the extending platform. You can see the pattern of square embeds are extended as well. Given that nothing was ever mounted to these, it may have something to do with supporting the roof of the trench. I'm sure someone in the comments will have a better idea of what's going on here. Along with the roof, they also completed the grade beams for the walls along the exit of the trench. These are several feet thick and have poles sticking up to allow safety rails to be installed. Another detail worth pointing out is that there is no underground diaphragm wall present at the far end of the trench. Instead, there is only a surface-level grade beam joining the 2 sides together. This made it much easier to install deluge piping later on. It took a full month to complete this phase of the project, and once the roof beam hardened enough to be able to support its own weight, they were finally able to begin excavating the inside of the trench. The first step to this involved breaking out all of the concrete from the working layer on the inner wall of the trench. This includes the square pad in the mouth of the trench and shaving down the strip along the grade beams to eliminate any overhang. Thanks to the deep soil mixing process, the ramp into the trench was far more stable than it would have been with native soil. Even though the hardened soilcrete was probably a bit more difficult to dig out, on the plus side, it created a nice, dry, stable surface for the excavators to travel down. The densified material removed from the trench was also perfect for use as backfill material around the perimeter of the walls. When we zoom in, you can see pretty clearly that the clumpy soil could almost be confused for gravel if you didn't know where it came from. The spoils were also used to form a driveway leading up to the mouth of the trench. I should mention that the area beneath the ramp also went through the same deep soil mixing process while the guide walls for the southern half of the diaphragm walls were being constructed. This was some good foresight to prevent the driveway from sinking over time under the weight of the heavy-duty test stand with Starship on top as they're moving back and forth. I'm sure some of you out there are probably experiencing that exact problem right now at your house. Anyway, before reaching the bottom of the trench, the slope flattens out and then steps down to the floor. Now that we can see the final depth of the trench, it really puts into perspective how insanely deep they constructed these diaphragm walls. As you can tell, whoever designed this was definitely not messing around. I'm no civil engineer, but I'd say that they probably over-engineered this just a bit to be absolutely certain that there was no way this supersized bathtub would be lifted out of the ground. After the excavation work was finished, the next step was to install underground pipes for the water deluge system. While not quite as large as the pipe used in the booster bidet system for Pad A, these are still pretty damn big. There are two sets of pipes that supply the flame bucket, with the large pipe being 48 inches in diameter, while the smaller one is 30 inches in diameter. After the sloped ramp was completed, a culvert was dug underneath the grade beam at the end of the trench, extending down to the bottom of the slope. The large pipes for the water deluge system were installed in this culvert and then buried before we ever had a chance to see them. There's an additional pipe used for pumping water out of the trench, which is not shown here. Part of the reason for the flat step at the bottom of the ramp is to allow the large water pipes to be fully covered instead of sticking out of the surface like they would have otherwise. With the pipes in place, they were able to begin laying out the rebar for the floor, step, and exit ramp. As you can probably guess, before filling it with concrete, long studded embed plates were added on the floor of the trench. We weren't able to see this process, but we can say with a decent amount of certainty that these exist. We will come back to that in a few minutes. While the concrete work for the flame trench was ongoing, other crews were simultaneously constructing several heavy-duty steel support structures. Let's quickly touch on each of them. First up was the large mobile static fire test stand, which eliminated their need for using cranes at the test site by allowing the ship to be transported back and forth between the flame trench and Megabay. I already did a pretty in-depth explanation of the features of the structure in the Evolution of Massey's episode. So instead of repeating that here again, let's start with the ship QD Gantry instead. This structure holds all of the plumbing that is routed to the ship. All of this was pre-installed on the ground before lifting it on top of the legs. Once completed, it was carried over to the trench and then lifted on top of the embed plates that we mentioned a few minutes ago. It was important to get this installed as quickly as possible to allow the GSE crews to finish connecting all of the cryo and high-pressure gas systems from the tank farm. At the time, I was really hoping this structure would have been covered with shielding, like the ship QD at the cryo testing station at the launch complex. But as I said in the Massey's Evolution episode, I don't think they ever expected it to become necessary. In retrospect, it's probably an over-exaggeration to describe this as a heavy-duty structure, given what happened to it after the explosion of Ship 36. As it turns out, it was nowhere near as strong as it appeared, but even with the shielding, I don't think it would have fared any better. Next up was the sliding service platform, which is a crucial component for allowing the static fire test stand to be operated without the need for a crane to lift the ship on and off of the test stand. This rectangular platform is fairly basic, consisting of 2 I-beams on either side with 8 cross-beams joining them together. There are also smaller square beams mounted around the perimeter, which act as a form for the deck. At one end of the platform, there are taller beams used to create a curb to prevent SPMTs from driving over the edge. Once the frame of the structure was completed, corrugated floor panels were mounted in the center and topped off with rebar before filling the deck with concrete. This actually held up fairly well for the most part during the Ship 36 incident, minus a few areas where the concrete was broken and had to be replaced. Luckily, the way this is designed allows it to be repaired rather easily as long as the steel frame isn't damaged. One thing we were not able to figure out for the longest time was the mechanism used to move the platform back and forth over the opening of the trench. You can see that the railing on the roof platform is basically just a square tube welded onto steel embed strips. This is extended on either side of the mouth of the trench with rails that are mounted to vertical steel plates with what are essentially railroad ties on top. The wheels are mounted to a rail on the bottom of the platform and are probably similar to ones you might find on a train. We were never able to verify this because they were installed sometime in the 19 days between when this image was taken and when the platform was lifted into position. Thanks to a recent unfortunate event, we were finally able to figure out how the platform is moved back and forth across the tracks. I guess you can say this is one positive thing that came out of the Ship 36 explosion. Before that incident, this little corner of the structure was always hidden from view by the Ship QD Gantry and the 4-foot step down to the roof platform. Without flying past the Ship QD Gantry or being directly above it, it's nearly impossible to see. Until recently, Mauricio from RGV Aerial had never attempted to do this because the shape of the river makes it very difficult to get a view from the south side without risking crossing into Mexico in the process. But after carefully threading the needle, he was able to capture the perfect shot that I've been waiting for more than a year. So thanks to these incredibly rare angles, we discovered 2 motors mounted on either side of the platform. As you can see, they were completely obliterated, but the remains were enough for us to put 2 and 2 together. With reduced TFR restrictions and an upgraded lens, Mauricio was able to capture high-quality images of the beams mounted to the side of the platform. Here you can see teeth running along the bottom of the beams, which helped us to finally solve this mystery. This is a typical rack and pinion mechanism that you might find on a 3D printer or an automatic sliding gate. We should have finally been able to see the wheels from this angle, but unfortunately they're covered by some sort of guard plates. Near the far end of the platform, there is a clevis bracket hanging from the bottom rail where the wheels are mounted. Below the pinion motor, you can see a linear actuator resting on the bracket. Once the platform is fully deployed over the mouth of the trench, this actuator extends outwards through the hole in the clevis bracket to lock it into position. This prevents the platform from slipping while the SPMTs are driving onto it. I have my doubts that the SPMT wheels would actually shift the platform, but it's better safe than sorry when it comes to that situation. You know, even though this episode is a year and a half late, it actually kind of worked out well because it gave us time to figure out some of these smaller details. I can't tell you how often I figure things out after releasing an episode and never have a convenient time to go back and mention them later. Anyway, after the sliding roof platform, we finally have the supporting framework for the flame deflector bucket, which was fabricated at SpaceX's McGregor testing facility before being shipped to Starbase. The lower part of the frame supports the curved section of the water deluge pipe manifold. As you can see, there are 4 speed core wall sections with cutouts along the curve to allow 6 U-shaped ribs to slot into position. For this application, speed core is a much better alternative to traditional reinforced concrete shear walls that are cast in place. On the inside of the vertical brackets, you can see studs welded to the inner walls. These act as shear connectors, which transfer forces between the steel and concrete to ensure the wall acts as a unified system. The hollow steel framing would easily be able to support the flame bucket on its own, but the concrete infill makes it far stronger than a normal concrete wall, even without the use of rebar. Other than the columns of the integration tower for Pad A, this is the first use of speed core structures at Starbase. But after discovering how incredibly versatile it is, they soon began to use it a lot more often. When it was time to construct the new vertical Raptor test stands at McGregor, they wanted to allow 2 Raptors to be tested side by side. They were already doing this on the horizontal test stand and the first vertical test stand constructed in 2020. But I think these structures may not have been offering enough protection against the occasional engine rub. So this time around, to protect the adjacent test cells and all of the GSE equipment, they constructed containment boxes out of speed core walls. Now that I think about it, it's actually kind of funny that the McGregor engineers put a lot more effort into protecting GSE equipment here than they did at Massey's. Anyway, after the U-shaped support beams were installed, smaller beams were welded between the ends of each of the ribs to increase stability. With the lower cradle assembly completed, they were now ready to install it at the bottom of the trench, which would have been a very interesting operation to witness. Looking at it from above, you can see that it's both longer and wider than the mouth of the trench. So fitting this structure through the opening would have required a fairly decent amount of finesse. Using 2 cranes working in tandem, the cradle would need to be tilted to one side and then rotated so it can fit through the hole. Once it's clear of the grade beams, it's rotated back in the opposite direction and then tilted back to the proper orientation. After beating the final level of the Tetris Championship, the entire perimeter of each wall section would have been welded down onto the embed plates. To support the slanted portion of the flame diverter bucket, there are 4 triangular walls that rest against the rear wall of the trench. Each of these triangular supports are constructed from 4 individual speed core sections that are stacked and welded together. Next, flat panels were welded to the front and back side of each of the walls. For clarification, these are laying on their backs in this image. The tops of each wall were left open to allow them to fill the structure with cement. The 2 outermost walls have 4-level access platforms mounted to them. There are ladders between each level to allow them to inspect different parts of the structure. For the inner walls, the access platforms were assembled separately. After flipping each of the sections to the proper orientation, the triangular frames were lifted into the trench one by one. The 3 remaining access platforms are located between each of the triangular wall sections. Once all of this was permanently welded to the embed plates, the upper cradle supports were mounted onto the support walls. These are much smaller than the lower cradle section, so they were able to be fully assembled at McGregor instead of doing it on site. But given their size, these also required cranes to perform a tandem lift to get them through the opening of the trench. I'm sure maneuvering these into place through that opening without colliding with the walls and supporting framework was quite the balancing act. After welding each section of the cradle to the support framework, they were finally able to fill the speed core walls with cement. The final and most important piece of the puzzle is the actual flame bucket, which was constructed in 3 massive sections before being transported to Starbase. It's important to reiterate that without the support from the McGregor facility, it would not have been possible to pull this project off as quickly as they did. I think it would have easily taken an additional 2 months to assemble this on site, which is something they could not afford. In March of 2024, the 3 gigantic pipe manifolds made the 460-mile trip to Starbase, and thanks to Starship Gazer being in the right place at the right time as they were arriving, we were able to make out some pretty awesome details. The 2 outer manifold sections are both constructed with 26 pipes that are 8 inches in diameter, while the centerpiece is a bit smaller and made with 14 pipes. Each section has a supply manifold at the bottom with a pattern of alternating holes punched through it. The pipes are inserted several inches through the holes before being welded on the outside of the manifold. After this, each pipe is permanently attached to its neighbor by welding it on both sides along the entire length to eliminate any gaps that may be present. At the top of each pipe is a threaded port. We initially believed these might just be for cleanout purposes or vents that allow gas to escape as the pipes are being welded. But given the plastic caps that are on them, it's possible that pressure sensors or additional nozzles were later installed in these locations. If they exist, these nozzles would likely be similar to the ones shown here. There are additional ports on the side of the smaller water manifold that may have nozzles installed in them as well. Honestly, I just can't see why this would be necessary, so I wouldn't be surprised if there was something else going on here. One thing the McGregor fabrication team left for them to do on site was drill holes into the pipes for the water jets. Shortly after they arrived, a 3-color pattern was painted onto the pipes to indicate the density of holes that needed to be drilled in each section. For example, in the red areas, you may have one hole every 3 inches, blue could be every 2 inches, and yellow might be a 1-inch separation. They more than likely drilled 2 rows of holes on each pipe to create an overlapping spray pattern instead of spraying straight outwards. I would imagine that all the areas without paint either don't get any holes drilled through them, or maybe they have the largest separation between holes, which could be 6 inches or more. We will come back to that shortly. Once all of the holes were completed, they were finally ready to install the flame bucket. Over a period of about 7 days, the 3 sections were lifted into the trench. The 2 side sections were installed first, followed by a pipe to join the 2 water manifolds. The middle section was lowered in after and rests on top and in front of the added pipe section. To secure the bucket in place, it's welded to the beams of the support cradle. That's quite a lot of welding considering they probably attach it on both sides of each of the 12 U-shaped beams. This is where those access platforms come in handy, so they can easily climb up to the areas where they need to perform all this welding. It's also helpful for periodic maintenance and inspections. An important detail to note about the design of the bucket is that the 2 side sections are supplied by the larger 48-inch pipe, while the middle section is connected to the smaller 30-inch pipe. There will actually be the same volume of water supplied to each section of the manifold. But given that the 2 outer sections both have 26 pipes, while the center section has 14, there will be 36% less water being discharged by each of the pipes in the 2 side sections. This means we should expect there to be 156% more holes in the middle section than there are in the 2 outer sections. This makes sense considering it will have 1 RVAC and 3 center engines firing down on it, while the side sections will get 1 RVAC each. With that said, even though we weren't able to see the full pattern on the one section where the paint was visible, we can still form a reasonable guess on what it looks like. When we overlay the position of the engines, it's easier to imagine this as a heat map based on engine position. It's very important to make sure there is more water coming from the areas that will have the greatest interaction with the individual exhaust plumes in order to maximize the amount of heat that is absorbed and dissipated. Anyway, less than a week after these were lifted into place, and presumably while they were still welding the bucket to the support cradle, Ship 26 was rolled out to Massey's to commission the new test stand. But it would end up sitting on top of the flame trench for nearly a full month until all of the propellant distribution systems were ready. In the meantime, they installed the final component of the water system in the trench. For this, they constructed a box to sit in the front left corner of the trench. Although we can't confirm, there's likely a small pit under the box to allow water to collect in a sump. The box has 2 compartments, one for a pump and the other may contain a filtration system. That way, after each test, they can recycle clean water back to the storage tanks. I think for this to work properly, the entire floor of the trench would have to be sloped towards the front corner. But even if it's not, they should still be able to get most of the water out each time. From start to finish, the construction of the flame trench took just under 6 months. This could have easily been an 8 to 12 month job had they not allowed for certain operations to overlap each other. Now, before we go into detail about the first of its kind water deluge system, let's take a quick historical look at water deluge system design. Now, I'm not going to focus on the discharge side of the deluge system, aka flame diverters and the arrangement of rainbirds and water nozzles, because there are so many different variations that it would take more time than it's worth. Instead, we will focus on the water delivery method, which is what makes this system at Massey's so unique. If that sounds boring to you, that's because it is. Over the past 60 years, there hasn't been much innovation in this area. The basic goal of the water supply system is to instantaneously supply massive volumes of water to the flame diverter and sound suppression systems. If you were to ask a random person off the street what they would use to deliver hundreds of thousands of gallons of water in less than a minute, the most common response would be a large mechanical water pump. And this makes sense, considering a majority of municipal water systems use industrial high-flow centrifugal or turbine pumps to supply thousands of homes and businesses at the same time. While this is probably the least ideal method for a water deluge system, industrial water pumps have in fact been used for this purpose historically. The best example of this is the infamous B1 and B2 test stands at the Stennis Space Center in Mississippi. The pump station for these test stands is located a quarter of a mile away next to a 66 million gallon reservoir. After some upgrades completed in 2015, this facility has the capability of supplying 330,000 gallons of water per minute through a single 8-foot pipe. When you think about that, the capacity of this reservoir is enough to run the deluge system for 3.5 hours straight, which is kind of absurd. That would mean you can perform 200 60-second static fire tests back-to-back before you actually drain the reservoir. To meet this demand, the facility uses 13 high-pressure water pumps, which are capable of discharging more than 33,000 gallons per minute at 300 psi. The power requirements for this are equally impressive. The pumps are driven by massive Nordberg V16 diesel engines, which you can see in this image from inside the facility. If the specs I mentioned are correct, then the pumps are being operated at around 75% of their maximum output, which is pretty standard for heavy machinery. This helps to reduce wear on the equipment while simultaneously adding a bit of redundancy. With that said, as I'm sure you can probably imagine, this is a very expensive system to operate and maintain. Beyond that, a big downside to using pump-driven systems is the potential for mechanical failure. The likelihood of such a failure is greater with larger systems. To put that into perspective, the deluge system for SLS operates at 900,000 gallons per minute. To achieve this same performance with centrifugal pumps, the combined power of those pumps would need to be somewhere between 80 to 100,000 horsepower. So if you were to operate this deluge system using the same components as Stennis, you would need 34 pumps and generators, and the facility would be more than 2.5 times larger. Losing multiple pumps during a launch would likely result in damage to the flame deflector, other areas of the pad, and potentially the payload as well, depending on how sensitive the equipment is. One factor that can contribute to causing mechanical issues with these types of pumps is the vibration environment created by extremely powerful rocket engines. This is part of the reason why most facilities that use diesel pumps for their water deluge systems have them located far away from the launch pad. At Cape Canaveral, there are several pump stations feeding various launch pads, many of which are no longer in use. For example, Pump Station 1 supplied water to launch complexes 5, 6, 17, 18, and 26. SLC 40 and SLC 41 share Pump Station 7, located in the middle of the two pads. By the look of the water manifold entering the station, this likely has 6 diesel-driven pumps that supply water to both pads. So this is just under half of the size and capacity of the system at Stennis. Due to the cost and risk associated with pump-driven systems, they are a lot less likely to be used as direct water sources for modern deluge systems. Besides the ones I've already mentioned, the only other facility I was able to find that currently employs this type of system is the Baikonur Cosmodrome in Kazakhstan. I'm sure there are probably some in India and China as well, but good luck finding information on those. For the most part, it seems like there is an unspoken consensus that has developed within the industry, and most launch providers have decided that it doesn't make sense to use expensive mechanical pumps to supply massive volumes of water when you can use gravity instead for a fraction of the cost. So at most launch sites around the world, you will find a large water tower somewhere within the general vicinity of the launch pad. At the Wallops Launch Complex in Virginia, you can find one at the Firefly Alpha launch pad. Rocket Lab has 2 water towers, one for Electron and a brand new one for their Neutron launch pad. Ariane Space has one for its Ariane 5 launch pad at the French Guiana Space Center. And then of course there's Cape Canaveral, aka the busiest launch complex on the planet. As I was doing research for this episode, I expected to see a lot more water towers out here than I actually ended up finding. But I think this is because some of these launch pads, like LC-37, where ULA launched the Delta IV Heavy before it was retired, do not use deluge systems at all. I'm sure someone in the comments will correct me if I'm wrong, but I was honestly a bit surprised to discover this. With a few exceptions, and excluding anything that came after 2021, all of the pads that are known to have deluge systems either use industrial pump stations or have a water tower on site. One of the most notable is Launch Complex 39B. This water tower was installed at the start of the Space Shuttle program and is now being used for SLS. There is an identical water tower at 39A, which is still partially being used for Falcon 9 launches. These systems are extremely reliable due to their simplicity, which is why they are the most common method for supplying water for deluge systems. So let's take a quick look at how they work. Using the tower at 39B as an example, there is a single large pipe coming down from the storage tank, which is split into smaller pipes that are routed to different parts of the deluge system. At the base of the tower, the main supply is split in half and then branches off into 3 smaller pipes on each side. Each of these pipes has a control valve, and after the valve, it joins back up into two main supply pipes that run to the pad. One of these lines supplies the rainbirds at the top of the flame diverter and the middle riser that sticks up from the side of the trench. This is routed through the mobile launcher and feeds the nozzles that are below each of the SRBs and the main engines. Together, these create a two-tiered system that suppresses sound and cools the exhaust plume. The second supply splits between the other two risers on either side of the middle one. These also attach to the bottom of the mobile launcher and feed the 5 rainbird nozzles on the launch deck. These are primarily meant to protect the surface of the mobile launch platform so it doesn't get melted by those SRBs after liftoff. When they're ready to begin sending water to the launch pad, they simply open up the valves on the manifold at the base of the water tower. The flow rate of water is controlled by the number of valves open. So there are essentially 3 settings for each side. When you know what to look for, you can actually see the moment the second and third valves are opened. The pressure of the water being supplied to the launch pad is determined by the height of the storage vessel. The towers at 39A and B are both 290 feet tall. The tower at 39A has a max capacity of 300,000 gallons, while the tower at 39B can hold nearly 450,000 gallons. This is thanks in part to structural upgrades to the tower and storage vessel to allow it to support the additional 150,000 gallons of water. Bigger and more powerful rockets require more water to accomplish the same tasks. In the case of SLS, all of this water is released in less than 30 seconds. Amazingly, this still wasn't enough to suppress the massive overpressure from the SRBs during the Artemis 1 mission. Blue Origin's new Glenn launch pad at LC-36 features the tallest water tower in the spaceflight industry, sitting at a height of 351 feet. The 61-foot difference adds an additional 26 psi, bringing the hydrostatic pressure of this gravity-fed system up to 152 psi, or 10.5 bar. Considering SLS has nearly 2.5 times more thrust than New Glenn, I wonder if this tower might actually be better suited for 39B and vice versa. Alright, so now that we know how this is done everywhere else, let's take a look at SpaceX. Ever since SpaceX was founded in March of 2002, they have always managed to find ways to break away from the norm in every way possible. So when they realized that nearly every launch provider in the world agreed that the best way to run a deluge system was by using industrial water pumps or a giant water tower, I can only imagine that the conversation may have gone something like this.
All right, water deluge. It seems to be pretty straightforward. We'll just go ahead and use the pre-existing system. So unless anybody has something they'd like to add, we'll go ahead and move on to Strongback GSE design review.
All right, look, everybody already knows where I stand on this situation. We're trying to get to Mars, okay? And we're not going to do that by following in the footsteps of anybody else out there. All right? So I say, f*** that. Let's focus on getting Falcon 9 reliable for now, but eventually, we're going to need to innovate water. As I mentioned earlier, the LC-40 launch pad, which SpaceX acquired after the end of the Titan IV program, was originally designed with a pump-driven system that was shared with LC-41. The existing system worked fine enough just to get the ball rolling with Falcon 9, but they would eventually wind up with a convenient opportunity to replace it with something else. Sometime after the Amos 6 anomaly in 2016, which damaged a lot of the pad infrastructure, the original system was upgraded to use a high-pressure gas-driven system. As far as I know, the water is still supplied from Pump Station 7, but instead of going directly to the deluge system, it's stored in 4 horizontal water tanks located near the pad. In place of water pumps, you can see several banks of high-pressure gas cylinders behind the water tanks. To pre-charge the system, liquid nitrogen is pumped through this vaporizer using a high-pressure pump like the one shown here. The high-pressure gas generated during this process, which is probably somewhere between 2,000 and 3,000 psi, is stored in the cylinder banks until it's ready to be unleashed. This process likely happens several hours, if not days in advance of the launch. It's a fairly slow gas generation system. A few seconds before ignition, the gas is released into the water tanks and immediately begins to force the water out through the deluge system under the vehicle and the rainbirds on either side of the pad. With SpaceX's second operational launch pad, at Space Launch Complex 4 in Vandenberg, most of the water distribution system is a mystery. According to one of the stories mentioned in the book Re-Entry by Eric Berger, SLC-4's water is supplied by an industrial pump station located away from the launch complex. I wasn't able to find it though, which I guess isn't all that surprising. When the site first became active, there was a water system inside of the trench which began dumping water several minutes before ignition. I think this is intended to create a large pool of water at the bottom of the trench, which is immediately blasted out as soon as the engines are ignited. There are additional nozzles above the exit of the trench that spray water down into the exhaust plume. For the actual launch pad, there are Rainbird nozzles pointing at the base of the vehicle. After the Iridium Next 4 launch in 2018, they added additional Rainbirds on either side of the strongback, which are activated shortly before liftoff. These seem to be similar to the gas-powered systems at LC-40, where nitrogen gas stored in high-pressure gas cylinders is used to force water out of the storage tanks that the Rainbirds are sticking out of. So this is like two separate systems in one. SpaceX's third Falcon 9 launch site, Pad 39A, actually has two separate systems as well. The Rainbirds are fed by the pre-existing water tower, but the Deluge system above the flame trench is supplied by a small gas-driven system next to the crew access tower. Honestly, I'm not sure why this was necessary. The water tower should have more than enough capacity to supply both systems, so this might have something to do with Falcon Heavy. In 2019, another gas-driven system similar in size to the one at SLC-40 was installed at Pad 39A for what was originally intended to become the first Starship test stand. This was never actually used, of course, and was eventually removed and sent to Starbase. After salvaging everything that was usable, they created a much more powerful version of this system after the first integrated flight test. Oddly, the number of high-pressure gas cylinders used here is significantly less than the system at LC-40. I'm not really sure what to make of that, though. Anyway, there are many advantages to a system like this. For one, you don't need a massive water tower. If you decide to upscale the system in the future, you just add more water tanks. If you want to increase the maximum discharge pressure, you can increase the capacity of the gas storage system. With a water tower, you would be forced to build a taller tower to increase the hydrostatic pressure. Since the pre-charge process occurs hours or maybe even days in advance, it's already available when it's needed. Because there are no pumps involved, you don't have to worry about mechanical components failing during operation. If the valves don't open, you simply abort the launch. So when it was time to construct the Starship test stand at Massey's, we initially expected that they would use the same system again. But it appears that someone was thoroughly unimpressed with how long it takes to pre-charge all 145 high-pressure gas cylinders and no longer had the patience for that operation. This time around, they wanted to incorporate an active gas generation system that could do it on the fly. In February of 2024, the main components for the water distribution system began arriving at Massey's. This included 3 lightly used water tanks, each with a capacity of 89,400 gallons. These definitely appeared to have seen better days, but nothing a little paint can't fix. Next to the water tank are 3 relatively small water pumps, a vertical liquid nitrogen storage tank, 9 high-pressure gas storage cylinders, and 4 heat exchanger tubes. These shell and tube heat exchangers are used to transfer heat from one fluid into another and are the key component of this system, so let's take a look at them. There are 6 subcomponents that make up these heat exchangers. First, we have the shell, which is a cylindrical vessel with 2 flanges on either end to allow water to enter the shell from one side and exit through the other. Inside the shell is a bundle of parallel tubes that bend and loop around so they start and finish at the opened end of the shell. These are attached to a perforated tube plate. The tube plate is sandwiched between the shell and the header, which has an inlet flange on the bottom and an outlet flange on the top for the second fluid. In this case, that second fluid will be nitrogen. To separate the incoming and outgoing fluid, there is a partition wall in the middle of the header that divides the vessel into 2 chambers. After entering the lower chamber, cryogenic liquid nitrogen is forced through the tubes, which are submerged in warm water. As it passes over the tubes, heat from the water is transferred into the liquid nitrogen, which causes it to boil. By the time the nitrogen finishes passing through the tubes, the liquid is completely vaporized and exits the upper chamber of the header as a gas. The final component is the perforated baffle plates, which are evenly spaced out inside of the shell. The baffles direct the water in a zigzag pattern across the tubes, which increases the turbulence and improves heat transfer efficiency. Each of these massive, water recirculating cryogenic vaporizers weigh just over 30,000 pounds. These are far larger than anything I was able to find online, but knowing their weight allows us to estimate the performance capabilities by extrapolating from known specifications of smaller models. But that will become more relevant later. With that said, each unit should be able to handle up to 16,000 gallons of water per minute. The liquid nitrogen is supplied to the vaporizers from the vertical storage tank, and the gaseous nitrogen discharged from the top of each vessel is combined into a common manifold, which is then routed underneath the water tanks. Next to each of the water tanks is a gas distribution manifold, which can either send nitrogen up into the tanks or out through the vents. The gas being supplied to each tank is split between two smaller diameter pipes, which recombine back into a larger pipe. The function of this is similar to the valves we discussed on the water tower example. There is another pair of split valves for the vent as well. The water discharge manifold for the first tank is connected to the 30-inch pipe for the middle section of the flame bucket. The middle tank is connected directly to the 48-inch pipe, which supplies the two outer sections. And finally, the last tank is connected to the heat exchangers to supply process water for the gas generation system. At the end of the water inlet manifold, there's a U-shaped pipe connected to the water outlet manifold. This allows some of the water to bypass the heat exchanger. We will discuss that more later. The water discharged from the heat exchangers is then connected to the same 48-inch pipe as the middle tank. On each of the three discharge manifolds, there is a large main valve and a smaller bypass valve, which is likely only used for initial flooding of the pipes going into the flame bucket. So, how does all of this work? Some of you have probably already figured out the general concept based on my description of the components. But for everyone else, the easiest way to explain is to just walk our way through the process from start to finish. When tankers arrive to deliver water, the first pump is used to offload water from the tankers into the three large storage tanks. There is a common manifold that connects to all three tanks, so they're all filled at the same time. If there happens to be more water in one tank, then it will slowly equalize with the others as they're being filled. As far as I can tell, as long as there is water in the tanks, the discharge lines will be flooded at all times, all the way up to the main and bypass valves. To help jumpstart the system, the water tanks are pre-pressurized in advance of the Deluge system activation. For this, they tap into the same high-pressure nitrogen supply that's being sent to all of the cryogenic storage tanks and nearly every pneumatic valve on site. I'm not going to explain that part in depth because I covered it in the Evolution of Massey's episode. This nitrogen line runs alongside the larger gas manifold under the water tanks. After branching off towards each of the individual valve manifolds, it splits into two smaller pipes that are attached after the first pair of red valves. Both sets of red valves will be closed at this time, so after opening these tiny yellow valves, nitrogen is slowly injected into the tanks until they reach the desired pressure. This is just enough pressure to kickstart the system. Now back to the water pumps. The two remaining pumps pull water from a location just before the main valve for the first water tank. This water is then pumped back to the tank. As best I can tell, this is used to cycle a small amount of water through the heat exchangers before the liquid nitrogen is introduced. Honestly, I'm not really sure how effective this is because of that U-shaped bypass that I mentioned a few minutes ago. There doesn't appear to be a valve to prevent the water from flowing through this bypass. Without that, I suspect the water is more likely to go through the bypass instead of being pulled through the heat exchanger. I think there's probably some minimum flow rate that has to be achieved before this is no longer the path of least resistance. Shortly before the system is ready to be activated, the bypass valves on each of the discharge manifolds should open up to allow water to begin flooding the pipes. They probably don't want to open this up too long in advance because it will eventually start flowing out of the holes in the flame bucket thanks to the fact that the tanks are several meters above the top of the bucket. Opening the bypass valve on the first tank should be enough to get water to start circulating through the vaporizers. This is a bit confusing because I'm pretty sure it would accomplish the same job as the water pumps, but it would likely be even more effective given the larger pipe diameter. So I'm probably missing something here because I don't understand why these pumps are necessary at all. Anyway, after this, high-pressure nitrogen gas stored in these cylinders is used to pressurize the liquid nitrogen storage tank. This eliminates the need for using pumps to circulate liquid nitrogen through the coils. Once the isolation valves on the discharge side of the tanks are opened, liquid nitrogen will begin flowing into each of the heat exchangers. As soon as the liquid nitrogen enters the coiled tubes, it will immediately begin to boil as it's heated by the warm water bath. Liquid nitrogen has a 694:1 expansion ratio, so this rapid vaporization will produce a tremendous amount of gas. Contrary to your natural intuition, this expansion does not result in an increase in pressure. Instead, the pressure of the gas leaving the vaporizer will be the same as the pressure of the liquid entering the tubes. This is why it's important for constant pressure to be maintained in the liquid nitrogen tank. I think as soon as this reaction begins, all three main water valves should open up, and the bypass valves will be closed shortly after. From this point on, the first tank will essentially be driving the entire system. As the rate of water being pushed through the vaporizer circuit quickly increases up to an estimated 80,000 gallons per minute, simultaneously, liquid nitrogen flow rate should increase proportionally with the water. So the system is able to generate enough gas to maintain pressure inside of the water tanks. I think one major benefit of this active gas generation system is that it allows them to precisely control the flow of water to the flame bucket. With gravity-driven systems like the one at LC39B, you only have three settings: low, medium, and high, which is determined by the number of valves open. Here, there are multiple ways for them to control the flow of water. For more precise control, they can adjust the pressure and therefore the flow rate of liquid nitrogen into the heat exchangers to control the amount of gas being generated. With a bit of tuning, they can probably dial in the exact pressure they want exiting the flame bucket down to within 1 psi, and they might even be able to throttle it up and down with the engines. To quickly step the pressure up and down, they can open 1, 2, or 3 relief valves on the gas discharge manifold, and at each of the tanks, they can open one or both main supply valves and one of the split valves for the vents as well. And finally, there are relief valves on each of the water tanks. So in total, that's like 6 different flow settings, but I'm not sure if they're actually used this way. When they're ready to de-energize the system, all of the depress vents I just mentioned are opened up to quickly bleed off the pressure in the tanks until it's safe to shut in the main water discharge valves. Lastly, the Deluge system shutdown won't occur until a few seconds after all 6 engines of the ship are no longer firing. If we compare it to the system at Pad A, then we can probably assume that it takes around 15 seconds for it to stop completely. Because of this, there will be a lot of water left down at the bottom of the trench. Using the sump pump at the base of the flame bucket, the remaining water is filtered and pumped back to the storage tanks. Just like the pump at the offloading station, it fills all 3 tanks at the same time. When SpaceX finally commissioned this system in June of 2024, all of the starships that were in various stages of completion at the time were able to breathe a collective sigh of relief. No more firing 6 extremely powerful rocket engines from 8 meters above a flat surface. By redirecting the plume away from the vehicle, they no longer had to worry about damage from shockwaves and debris being rebounded up into the skirt of the ship. Equally important, they were now able to perform longer duration tests without having to worry about damaging the concrete blast surface in the process. And perhaps my favorite thing about this was the ability to have clean views looking up into the skirt of the vehicle during static fire tests, allowing us to view the ignition sequence and engine gimbling in slow motion. This was a massive improvement from operations at the suborbital test stands, and was about to get even better. Starting in January of 2025, SpaceX made a series of upgrades to the Flame Trench and Water Deluge system. First, they swapped out the liquid nitrogen tank and installed a larger one in its place. Without knowing the exact capacity of each tank, it appears to be roughly 4 to 5 times larger than the original. Around the same time, they also increased the amount of high-pressure gas cylinders used to charge the tank. If you were ever wondering how all of a sudden they went from performing 7-second static fire tests to performing long-duration tests that last for up to 60 seconds, well, now you know. The original liquid nitrogen tank was not big enough to allow them to make use of the full capacity of water stored between the 3 tanks. Another interesting thing to note is that they have space for 5 heat exchangers but ended up removing one before it was ever connected with the others. And thanks to recent images from the southern side of the facility, we can see that they apparently only have nitrogen running to 3 out of the 4 remaining heat exchangers. So the 4th one is essentially being used as a bypass to the heat exchangers, which reduces the total volume of gas being generated by 25%. If I had to guess, they probably did this after realizing they were producing way more gas than necessary during the initial tests of the system. The reason this heat exchanger wasn't just removed altogether likely has something to do with maintaining the desired flow rate of water to the outer sections of the flame bucket. If each of these heat exchangers can handle roughly 15,000 gallons per minute, and the bypass pipe can only handle 30,000 gallons per minute, then completely removing that heat exchanger would limit them to a maximum of 75,000 gallons per minute. To stay at 90,000 gallons per minute, they would need to leave this in, or increase the size of the bypass. I think the reason they didn't go that route was to allow them to quickly upgrade the gas generation capacity of the system if it becomes necessary. I have a feeling that when they begin testing vehicles with the upgraded Raptor 3 engines, they may end up needing that 4th heat exchanger to boost the pressure of the system to match the 14% increase in thrust of the V3 ships. And they will probably need all 5 when they eventually begin incorporating 6 RVACs on the version 4 ships. That 68% increase in thrust will more than likely require some adjustment to the hole patterns on the outer sections of the flame bucket, and maybe even an upgrade in water capacity. Speaking of upgrades, in March of 2025, after their 5th static fire test on the new flame trench, SpaceX realized that they probably needed to add some protection around the mouth of the trench. Even though the exhaust plume does not directly contact the walls, the column of fire passing through might as well be the gates of hell. The concrete and tracks for the roof platform are exposed to some pretty intense heating. Luckily, they planned ahead when forming the mouth of the trench when they added the steel embed strips into the top and bottom edges of the opening. This allowed them to easily mount protective steel panels to cover all of the exposed concrete on the front and back faces. On the sides, they installed protective covers on the mounting brackets for the rail track. Finally, they added a pipe just below each of the rails. Just like the flame bucket, these have holes punched into them which spray water towards the rails to keep them cool. The last thing you would want is for the ship to end up stranded on the test stand while they repair damaged railing resulting from intense thermal cycling. You can actually see these nozzles spraying during the single-engine static fire test of Ship 35. Each of these pipes is attached to the water manifolds at the bottom of the trench. There's another big upgrade to this trench that I've been waiting on for more than a full year that still hasn't happened yet. Even though the Deluge system seems to do a really good job of cooling the exhaust plume, the steam produced during these tests is still pretty damn hot. Over time, this will cause spalling damage to the exposed concrete walls of the trench. After less than 10 static fire tests, you can already see where chips of concrete have broken free. I'm sure some of what we're seeing here is the natural surface texture from the construction process, but not all of it. Similar to the protective shielding they installed at the base of the integration tower in early 2021, I've been hoping that these steel panels sitting on the side of location for the last year were a sign that they would eventually do the same thing for the walls of the flame trench, but that hasn't happened yet. When it comes to reducing the likelihood of costly repairs in the future, this seems like the way to go. And speaking of costly repairs, 1 year and 13 days after the new flame trench was commissioned, Murphy's Law fulfilled its promise by throwing a diabolical curveball that no one saw coming. As all of you know by now, none of the infrastructure at Massey's was designed to withstand this type of anomaly. In the aftermath of the explosion of Ship 36, one minor flaw of this flame bucket design became painfully clear. Thanks to these images from Interstellar Gateway, we can see that, as it exploded, Ship 36 sharded out several of its engines and the entire thrust puck into the flame trench. When multiple 2-ton engines impact the flame bucket, it's bound to cause some collateral damage. Because of the way these flame buckets are assembled, it's not very easy to make repairs, or at least not in the most ideal fashion. As an example, let's say that one of the RVACs partially crushes one of the pipes in this area. Then you would probably end up needing to replace this entire section of pipes. I'm going to simplify this down to removing a single pipe because that makes it a bit easier to get the point across. When cutting this section out, it's easy enough to make cuts along the circumference of the pipes and to cut the welds that secure it to the cradle supports. But separating it from the two adjacent pipes is where you might run into some problems. I'm not sure how deep these welds actually go, but it might be difficult to make a clean cut without damaging the good pipe. But I guess that depends on what kind of tool you use to do it. You could offset the cut a few millimeters away from the weld and then shave down everything that's remaining afterwards, but that would be quite the process. Now when you go to add in the new pipe section, there's another problem. Once again, you can easily perform the weld around most of the circumference, but there's about 15 degrees on either side where it's basically impossible to reach. To avoid this, you would have to remove the entire length of the pipe all the way down to just before where it connects to the manifold, in a location where you can access the full circumference of the pipe. In my opinion, this method makes the most sense assuming you're able to remove it without damaging its neighbors. But instead of cutting out the full pipe sections, they cut out just the parts that were actually damaged on the upward-facing side. Then they cut identical sections out of spare pipes that were overnighted from McGregor, and then used them to patch the areas that were removed from the flame bucket. Honestly, I'm sure it's fine, but I never would have believed this if I didn't see it with my own eyes. You can actually see them in the process of doing this thanks to a well-timed shot from RGV Aerial. While this sounds kind of crazy, I'm sure there's a reason the repairs were done this way. It might look super ugly if you saw it up close, but as long as it gets the job done, I guess that's all that matters. The good news is, the chances of a repeat incident happening in the future are incredibly low. Overall, the design of this water deluge system is pretty awesome, and I'm honestly surprised that no one has ever attempted something like this before. Heat exchangers aren't exactly new technology, but as far as I know, they have never been applied in this way, which is why this system is so unique. Clearly happy with its performance, the GSE engineers at McGregor decided that they wanted this system for themselves, which isn't surprising considering they were the ones who designed it in the first place. The McGregor testing facility is like a water deluge museum. The Falcon 9 test stand and tripod stand both share a water tower, and the Falcon 9 Stage 2 test stand has its own water tower as well. The Merlin test stand has a large pool with pumps for filling vertical storage tanks. These either use gravity or gas injection to supply the flame bucket, but it's difficult to tell. The horizontal Raptor stand is a mystery, but the vertical test stand uses a horizontal tank and high-pressure gas cylinders. And finally, when SpaceX began constructing 2 brand new vertical Raptor test stands in July of 2024, both flame trenches were outfitted with near identical systems as the one developed for Massey's. The trenches for the Raptor test stand are much deeper, and the flame buckets are a bit taller as well. The only difference is that these are single-engine tests, so they don't need as much water. Because of that, this system is scaled down to use a single vaporizer instead of 3. Since the system at Massey's seemed to be a proof of concept for their other test stands, we expected that it would likely be duplicated and scaled up for the new version 2 launch pad at Starbase. But as it turns out, SpaceX had something way more aggressive up their sleeves. If I had to guess, someone from the Raptor Propulsions team decided to switch over to GSE engineering because the new system design for Stage 0 2.0 is absolutely ridiculous. I highly doubt it could have been conceived by anyone else. On the next deep dive investigation, we will take a look at the next evolution of Starship Flame Trenches, where SpaceX has apparently graduated to using baby Raptor engines to power their water deluge system. I promise you won't want to miss that episode, so make sure you're subscribed to the channel if you aren't already. As you can tell, a massive amount of effort went into explaining this topic in a way that was easy to digest. If you enjoyed this episode and would like to support the channel, then please consider becoming a monthly member on Patreon. This is by far the best way to help us continue to do what we do at this channel. This allows us to compensate people like Ryan Hansen Space, who put in massive amounts of time creating the renders and animations that are critical for helping us explain these topics. In case it wasn't already obvious, it would have been impossible for us to create this episode without the amazing aerial documentation of Starbase by RGV Aerial. So please consider supporting him as well, or checking out the Starbase weekly live streams on his YouTube channel, where we review the latest flyover images every week. Before we go, I also want to give a huge shout out to Starship Gazer, the teams at Lab Padre and NASA Spaceflight, and everyone else whose content was used in today's investigation. Last but not least, thank you to Opera for sponsoring this episode. Don't forget to click on the link in the description to download the Opera browser for free. Alright everyone, that's my time for today. Hope to see you on the next deep dive investigation. For now, this is Stage 0 Zach, signing off.